Partho Das, Assistant Professor, Department of Electrical Engineering, JS College of Engineering, West Bengal, India. So, welcome to my class. Today's topic is Thevenin's theorem. Okay, so today we are going to solve this particular theorem. So in this particular theorem we are going to solve, so we are going to see what is the statement of this theorem, then we are going to see what are the conditions to apply this theorem, then we are going to see what are the steps to solve this particular theorem, and at the end we can see that what are the advantages and disadvantages of this particular theorem. So coming to first to the definition of the Thevenin's theorem. So in Thevenin's theorem it is told that a Thevenin's theorem in any complex circuit can be simplified to a simple series circuit where which contains a voltage source, equivalent resistance and the load resistance connected in series, and we can find out the load current or load voltage across any branch of any complicated circuit. That means whenever we have a complex circuit or bigger one circuit and we want to find out the current passing through any particular branch, there we can apply this particular theorem, that is Thevenin's theorem, and by which we can directly find out what is the value of the current and voltage through a particular branch. Okay, so this is the theorem. So next we are coming to the conditions to apply the Thevenin's theorem. So the conditions are that the first one is that the complex one, that we are going to reduce to a simple series circuit, and next thing is that the circuit should be linear and the circuit should be bilateral. So what do you mean by this linear and bilateral? So linear means a circuit which contains some linear elements. Now what is linear elements? Linear elements means element which has a linear VI characteristics. That means with the increasing value of voltage, say consider a resistor. Okay, so now give a supply to this one. If we give 10 volt supply, say 0.1 ampere current is flowing. Now if we increase the voltage value, so what will is going to happen? So the current value is going to be increased, say. Okay, so if this is increasing, that means with the increasing value of voltage that current is increasing, or decreasing value of voltage this current is decreasing, then it is a linear property. Okay, so then it is known as the linear element, and which a circuit which contains this kind of element is known as the linear circuit. Now coming to the next, that is what is bilateral element. What is bilateral element? Bilateral element. What is bilateral element? Bilateral means, from the name we can say that bi means both, so we can say that a circuit through which contains the bilateral element actually. And next we can say, and what is bilateral element? Element through which both direction current can flow. So that means actually already we have those things we have discussed in the previous theorems also. When we have done the superposition theorem, when we have done the Norton's theorem, there we have discussed. So say this is a resistor, and this potential is higher, this potential is lower, so definitely current will flow from this to this. Okay, now if we change the terminal, that means if we make this one plus and this one minus, what will happen? The current will flow through this one. Then this element is known as the bilateral element. Bi means both direction current can flow, and due to that the property of this element does not get any change. So this is the bilateral property. So that means Thevenin's theorem can be applied where we can apply the circuit should be linear, the circuit should be bilateral, then the circuit must be a complex one, which we are going to solve to a simple series circuit which contains a simple voltage source, equivalent resistance and the load resistance connected in series. Okay, so these are the conditions. Now let us say how we can solve this theorem. So for that simplicity, for that understanding, say we are considering a circuit. Say this is our circuit. This is voltage, this is R1, R2, R3, and say this is RL. And according to Thevenin's theorem, we have to solve this particular circuit. So it is told that in Thevenin's theorem that whenever we have a circuit like this and we want to find out the current or voltage across any current through any branch or voltage across any branch, then what we have to do, we have to remove that terminal, load voltage, load resistance from there, and then find out what is the open terminal voltage. That is the purpose in the initial case. So now we are going to do that. So step 1, as per the rule is concerned, so what is the step 1? In step 1, we are going to remove the load resistance. So we are going to remove the load resistance and we will make the terminal open, and we will find out what is the open terminal voltage appearing across the open terminal. So first we are drawing the diagram. Yes, now this is our circuit. So this is the Thevenin's initial case we have to do. That means we have to remove the load resistance. Yes, we have removed. Made the terminal open. Yes, we have made the terminal open. And now find out what is the voltage appearing over this open terminal. So that will be our Thevenin's voltage. That is the open terminal voltage. That we have to do. Now, how we can do that one? So what is the voltage actually appears over here? So actually see, the current is producing from here, that is flowing like this, and at this node it will be divided. No, it will not divide because this terminal is open. So this open terminal is offering infinite amount of resistance, so no current will flow in this direction. Whatever current is flowing generating from here, it will flow like this in this loop only. Okay, so that means here there is no current, and according to Ohm's law, if there is no current, there is no voltage. So actually there is no voltage. So where is the voltage, and how we can find out some voltage over here? So the voltage is actually appearing across this parallel terminal, this terminal of this open terminal. Okay, so now say whatever is the voltage appearing over here, that voltage is appearing over here. Okay, so if we can find out what is the voltage across over here, then we can find out what is the voltage across here. So what is the voltage over here? How we can find out that? See, we know that the voltage across any branch is equal to the V is equal to I into R. So R is already known, R2. So we have to find out I. Now if we find out I, then we can find out the voltage drop across this one. Now the point is, what is the I over here? Okay, so what is the I? So we can say that this is a simple series loop. If it is a simple series loop, so what is the equivalent resistance over here? Only two resistors are working over here, though it is present in the circuit, but it is not effective as the terminal is open. So we can say that R equivalent in this particular case is R1 plus R2 in ohm, correct? Now main, say this is I current. I is equal to total voltage by R equivalent. That will give us the main current of this. That current is coming to this node, then it is going like this. So I current is also flowing through this one. So if we say this is the AB node, so voltage across AB, what is the voltage? We can say that the voltage across AB is equal to current passing through AB terminal and the resistance across that one. So current passing through is I into this R2 will give us the voltage across this terminal, and that voltage is appearing over here, we can say now. So that voltage is known as VTH, that is known as Thevenin's voltage. Okay, so first we have to find out that means if we summarize what we have done, then we can say that we have removed the load resistance, we have made the terminal open, and we have finded out what is the voltage appearing across that open terminal. Now step 2. So now in step 2 it is told that make this circuit, after removing the load resistance, make this circuit independent of any kind of source and view from the open terminal from where we have disconnected the load, and find out what is the equivalent resistance of the circuit. Okay, so whatever it is told in the statement or in the theorem, that we will do. That means we have already removed, in the see this diagram, we have already removed the load resistance. Now it is told that whatever is the number of voltage source or currents, whatever is the number of sources actually, so that removed all those, leaving its internal resistance over there. So here considering we have a ideal voltage source. So if we have a ideal voltage source, if we remove that one, what we have to left over there? It is internal resistance. What is the internal resistance of an ideal voltage source? It is 0. So we have to, what we have to do, we have to make the terminal short. So that we will going to do. See, okay, so what is the resistance value over here? This is R1, this is R2, this is R3, correct? So these are the total resistance, and now it is told that view from this terminal, open terminal, and find out what is the total resistance of this particular circuit. So if we viewing means what? Viewing means if we think of, if some source is there and how if some source is present over there, then how the current is flowing through the circuit. What are the series parallel combinations of what is the series parallel combination of the resistances? So we can say that, so if we think of, so we can find out that, so if we think that the current is flowing like this, and in this node it is dividing, so these two are in parallel with that this one series, and inversely if we think that the current is flowing in this direction, then also we can say these two are in parallel with that this one in series. So the equivalent resistance for this particular step is equal to R1 R2 parallel with that R3 in series. So that is the total equivalent resistance of this particular case, and it is known as RTH. That is the Thevenin's resistance. Okay, so this is the Thevenin's resistance. Now last step, that means last thing we have to do for the solution of this particular problem. That means again coming back to the problem, what was our problem? We have to find out the current passing through this load resistance, and to do that, initially what we have done, we have removed the load resistance, we have made the terminals open, and we have finded out what is the open terminal voltage. So that is our Thevenin's voltage. Now coming to the step 2, there what we have done, we have finded out the equivalent resistance viewing from the open terminal of the circuit and finded out the Thevenin's resistance. Now the last step. So what is the last step? So step 3, we can say that in step 3 what we have to do, in step 3 whatever is the first step result. What is the first step result? This one is the first step result, that VTH. So that will act as equivalent voltage source for the simple series circuit. And so what is the step 2 result? This one, RTH. So that will be our series resistance of the circuit, and initially from the circuit we have disconnected this load resistance. So we have to connect this component in series with the other two components. So this is the rule for Thevenin's. That means VTH, that is the Thevenin's voltage, RTH, that is the Thevenin resistance, and load resistance, all should be connected in series with each other. So as per it is told in the theorem that I am going to draw. So this is, say, VTH, okay, and with that we have to connect in series this RTH. So we know the value, so there is no problem, and RL already we have disconnected from the circuit. Now see, this circuit is simplified to this one. correct. So this circuit can be simplified to this one. So now the point is, whatever is the circuit, I have taken for your better understanding, I have taken the smaller one. Now the circuit may be larger one also, okay. So then also the last step circuit will be always this kind of, that means the VTH, the RTH and RL all connected in series. Okay, so now if I say you the find out the what is the current passing through this load resistance, that means IL. So what we will write down, very simple, IL is equal to Ohm's law, VTH by RTH plus RL. Okay, so this is the current formula for finding out the load current passing through the any load of a circuit. So this is how we can solve Thevenin's theorem. So now I am going to consider a larger one circuit and let us see how we can solve. So the concept that we have to remember over here is that the first step we have to find out the VTH, second step we have to find out the RTH, and at the end we have to find out the load current or load voltage and power, whatever we want to find out, that we can find out. Okay, so let us erase this one and let us take a problem to solve with this Thevenin's theorem. So Thevenin's theorem is actually known as the voltage equivalent theorem. Why it is known as the voltage equivalent theorem? Because here, as we can see that we are in the initial stage, we are finding out the voltage over here. Okay, so we can say that this is the equivalent voltage theorem. So let us erase this one. It actually takes 20 to 30 seconds to dry out. Then if we use this eraser, it will be easier to erase. Okay, so let us take that as example. So say our circuit is like this. Yes, a larger one, so one loop is increased over here. So say again, there is a V, there is R1, this is R2, this is R3, this is R4, this is R5, and this is RL. And it is told that find out the current passing through this particular resistor, the load resistance. So as we have discussed previously that how to solve a Thevenin's theorem, so that procedure we are going to use over here. So step 1, what we are going to do, we are going to remove the load resistance, we will make the terminal open, and we are going to find out what is the voltage across that open terminal. Now, so first I am drawing that one. Yes, so this is our circuit. So there is a V, R1, R2, R3, R4, R5, and the load resistance has removed. Now our view, what is our view? We have to, our aim is to find out the voltage across this open terminal. So what is the voltage? First try to clear that concept. What is the voltage across this open terminal? The voltage across this open terminal is actually the voltage across this is R4. So first of all we have to find out the voltage across this R4. What is the voltage across this R4? That means the current flowing through this R4 into that resistance value will give us the voltage across this R4. So we can we say that from here the current will start to flow. So first node here, it will divide as per the resistance value. So that current will come to this node. Here it will not go, it has infinite resistance. So this direction the current will flow. So can we think of the circuit is like this? see this circuit actually I have drawn like this way. So the current will flow through R1. Yes, it is flowing. Then it is coming to some node. It is dividing between R2 and R3. It is dividing between R2 and R3. Whatever current is flowing through R3, that is current flowing through R4. So that is in series. So what is the equivalent resistance? So first, so what is our aim? Our aim is to find out what is the current flowing through this one. If we know that, we can find out what is the VTH. So to find out that, first we have to find out what is the main current. So here we have to find out what is the current. Then we will apply the current division rule to find out what is the branch current passing through this one. Okay, and after doing that, we know what is the current over there. So how to do that? The first, as we have done in the previous case, R equivalent we have to find out. So what is the R equivalent? That is this two are in series. With that, this R2 in parallel. With that, this R1 in series. Okay, so this R3 plus R4 in series. With that, this R2 in parallel. Okay, so this is R3 plus R4 plus R2, that one in series with this R1. So this is our total equivalent resistance. Okay, so now after finding out this total equivalent resistance, now what we can find out? So we can find out the main current, say the given name, that is I. So if we know, now we can find out the I is equal to that V by R equivalent value. So whatever we have find out. So now that we know the current passing up to this one. Now we have to find out this current. That means the given name, this is, say this is I3 current, and I3 current, that we have to find out. We don't have to find out what is the current passing through R2. So we definitely we're not going to do that. So we are going to find out this I3. Okay, so what is the current I3? We know what is that. That is the current division rule. So current division rule is stating that if we want to find out the I3 passing through this R3 plus R4, so then we have to consider the opposite parallel resistance, that is R2 over here. So the total current, that is I into opposite branch resistance by R2 plus R3 plus R4. So that will give us the current flowing through this R4. And after finding out that, the VTH is equal to, we can say that this I3 current, this is the I3 current into this R4. Okay, so that is in volt. Done. So that is about the first step. Now step 2. So in step 2, what we are going to do, again this circuit can be modified after removing the sources, and then we are going to find out what is the equivalent resistance of the circuit viewing from the output, the disconnected terminal, that is the open terminal. So here also we have a ideal voltage source. So after removing that ideal voltage source, what we are going to do, we have to make that terminal short. So that short that we have made, so that is R1, this is R2, this is R3, this is R4, this is R5, and we are viewing from here. Now if we are viewing from there, so what I have told, just think of some current is flowing through that one, then try to find out that which resistance are in series parallel combination. So if we think that the current is flowing like this, so first node, it is coming over here, then it is dividing. So can we draw like this? So first the current is flowing through R5, we have drawn. Okay, then that current is dividing between R3 and R4. Okay, so whatever current is flowing through R3, again at this node it is dividing between this R1 and R2. So this is R1, so this is R2. So the same thing I have drawn like this way for your better understanding. So now tell me, what is the series parallel combination? So first, these two are in parallel. With that, this R3 in series, as we can see over there, and this whole combination is again parallel with this R4, and this total combination is in series with this I5. Okay, so the first thing is that this R1, R2 are in parallel. Okay, so combination of R1, R2 we have written, and with that this R3 in series, correct, and this whole combination again with parallel with this R4. So R1 R2 by R1 plus R2 plus R3 plus R4. Okay, so first and the whole this whole combination is again in series with this R5. So can we write down this RTH is equal to this R5 plus this whole component will give us the total equivalent resistance of the circuit. So like this way we can find out any problem, we can solve any problem. So now at the we are reaching at the end. So at the end what we know, so that means now we know the VTH. So we have with us this VTH, we know with us we have this RTH, and initially from the circuit we have disconnected this RL. Okay, so now we will going to connect these three components and we are going to find out what is the total what is the load current passing through this load resistance. So step 3, sorry I have to change. So step 3. So in step 3 what we are going to do, the first step result, that is the VTH, second step that is the RTH, and initially we have disconnected this RL. So this is VTH, this is RTH, and this is RL. Okay, all values are known to us because we have all calculated. Okay, so find out this IL. So IL, can we write down Ohm's law, VTH by RTH plus RL? Yes, we can write down. Okay, so this is the current. Now if we want to find out the voltage, VL, so what is the voltage? So IL into RL will give us the voltage across this one. Okay, so like this way we can, by applying this Thevenin's theorem, we can simplify whatever is the complex circuit is present over there, and then we can simply reduce to that circuit to a simple series circuit, and then we can find out what is the current passing through a particular branch, or what is the voltage across in particular branch. So this is all about the Thevenin's theorem. Okay, so thank you.